We have Natalia Oliveros-Gomez, who's going to tell us about an informed and systematic method to identify variable L, T, and Y dwarfs.
Thank you. Can you hear me? Well, okay, perfect. Well, I include a little bit about L dwarf, but it's the same method that we apply for T, so I extend to L. Okay, I am first graduate student, just like finished 2 months ago in the Johns Hopkins University, and I want to start talking about the importance to study the variability. In this picture, we can see an example about Jupiter, that is our near object with variability that we can observe. And we notice that in different wavelengths in the upper and bottom figures, we have two different light curve in two different wavelengths. And we notice that the shape of the light curve is different because we notice different patterns and different structures in the atmosphere. So for Jupiter, we can make a relationship between the patterns and internal structures that we can have in the atmosphere and the shape of the light curve. So in the case of the brown dwarf, we can make exactly the same process, but we can make the contrary. We can measure the light curve, and in terms of that, we can estimate what is the behavior of the internal structure. And if we study in different wavelengths, we can make maps in different depths of the atmosphere of the brown dwarf, and at the end, obtain a 3D atmospheric map about what happened in the interior of the brown dwarf. So for that reason, it's important to study variable objects. So how do we know if a brown dwarf is variable or not? And the simple answer now is that we need to spend a lot of time, a lot of hours and resources to observe each individual object. So we need to observe during 5, 7 or more hours each object, and with the incertitude to have variable objects or non-variable objects. If it's a variable object, it's super great because we now have other object to observe in detail, and it's super cool, but we can obtain that it's non-variable, and in that case, not super cool. So for that is the reason for this informed and systematic method, because we want to detect the variability, but using a single near-infrared spectrum. So how we can do that? Our idea, we start analyzing time-resolved spectroscopy of a brown dwarf that we know like variable, and we study in detail what happened in different parts of the spectra, and using that, we design spectral indices, and we compare the indices between them and obtain some different variable and non-variable areas. And with the method complete, we pass to test the method. So this method is the answer to no more long hours to use to know if the object is variable or non-variable, because it's super important, save our time in the telescope, so it's super important. And also, you need one near-infrared spectrum. Now, the method is available to apply in L and T dwarf, but I obviously want at the end of the presentation mention what is our idea in the future for apply to Y dwarf. So, like I mentioned, we start designing the spectral indices. This is an example about, in red, two different regions that change more in comparison with the blue ones. So we made a ratio and we defined one indices, and we made the same in different windows of the spectra that we analyze. And we have 6 different indices for T dwarf and other 6 for L dwarf. And we compare the indices between them, and we notice that we have 2 groups, the red ones and the blue ones in this plot. And the meaning of the colors is basically in blue, we have the lowest variability, more near to 1, like if we have a flat or non-variable object, and in red, the highest variability spectra that we have for the same object. And taking into account this, we measure or we define the variability in areas using mathematical and computational tools to define exactly good variability areas. So, like a summary of the method, we use a near-infrared spectrum, we measure the indices of that spectrum of any object, and we compare in the index plot, and we have the question, in how many areas of variability the object falls. Depends of the number that we obtain, we can say if the object is a variable candidate or non-variable candidate. So with the method complete, we pass to test the method. In our case, we apply the method in 26 T dwarf and in 75 L dwarf using the SPEC catalog. We obtain these results. We obtain a variability fraction for the 51% for L dwarf and 38% for T dwarf. The number is important, but the most important thing here is the comparison with photometrically surveys. We have the comparison with this in these 3 articles that have a photometric survey using different telescope, different instruments, ground-based telescope, space telescope. So that's important because the numbers have a relation between them. So, but in our case, we only use a single near-infrared spectrum. And also, well, in our sample, we notice that some of that objects are in the literature, and we know because have photometric information about if it's variable or not variable object. So we use this information to obtain a recovery rate about our method, if works or not, and spoiler, works. We obtain around 70 and 80% to recovery rates from variable objects and 100% for non-variable objects, and a false negative around 15%. So basically, we can find the most of the variable objects, but also we can discard all the non-variable objects using these methods. And super important, we can save the time and resources to observe and obtain information about variability. So the important thing for the future now here is what is our idea to apply this method to white dwarf. So the sample answer is that we need more data. We need to follow 3 steps. The first one is that we need a time resolved spectroscopy about one white dwarf, like we know, like variable, because we need to identify possible parts of the spectra that change more than the others and design the indices. Also, we need known variables and non-variable objects because we need that for test the method and obtain recovery rates. And also we need a sample of white dwarf with one single near-infrared spectrum to obtain a list of new candidate variable brown dwarf. So here's where it's super important, the capabilities of the JWST, because it's possible using their instruments to study this type of objects. This is an example for the cycle 3 that we have this proposal from my advisor that we have time result. We want to have time result spectroscopy about ROS 458C. This is at T8.5. So in previous studies, we obtained that this object have variability in J and Y bands. So this is one of the objects that we can use to the key to start the possible indices for the TY transition objects, and also take into account other proposals that all of you are mentioning in previous talks that can help us to apply the method in the 3 different steps that we have to follow for design the method. So the most difficult part here is the step number 2, because we need also photometric surveys about white dwarf that it's a little bit difficult, but it's possible. And the idea is that in the future we can observe this type of object. So like a summary, we want to understand the atmospheres about brown dwarf. And for that reason, we need to study variable objects. So this method is super useful to obtain a variable candidates and save time to us. It now is available in GitHub, and also in this moment, it's possible to apply for objects between L4 and T7. And in the future, we want to extend the method to TY transition and Y dwarf. So we need more data. And if you want to see more details about the method or results, you can see in these two articles, one for T dwarf and the other for L dwarf. And that's it. If you have any question or you want to talk later, or I'm here. Thank you.
Natalia, thank you so much. So we have 3 minutes for questions. I'd like to encourage early career researchers to feel comfortable enough to ask questions as well.
There.
Carlos.
Really great talk. Kyle Franson, UT Austin. So I'm wondering, you showed the variability like rates on slide 8. I'm wondering why the variability rates through this method are kind of skewed to, so like the 51 plus 4 minus 38, like why they're very kind of skewed to lower bound, or there's a skew in the kind of low direction.
Yeah, well, all depends of the threshold that we define, because we have, in the case of T-dwarf, we have 12 plots, index plots. So we define the number in 9 for T-dwarf. So we define the number, I think that I have presented plot. No. So maybe this can be useful. So we define the threshold, for example, in a quantity of plots, and the majority of non-variables falls in the non-variable areas, but not all the variable objects falls in the variable areas. So that affect a result. But in our case, we prefer that discard a non-variable objects that obtain all the variable candidates. So that's the more important.
Time for one more question, and Hinara there.
Nice talk. Naro Suarez, American Museum of Natural History. So all this technique was tried using meeting for the spectra. So I wonder if you try meeting for the spectra, what would you expect? If the same recovery, or think about it?
Yeah, well, yeah. Now we are using near infrared spectrum because we design the indices using Hubble data. But yeah, in the future, we want to apply also, for example, in JWST, and maybe we can include more indices using mid-infrared spectra, because I remember one article yours that we use a silicate index to define how is the structure or something. So that can be useful to include maybe using other parts of the spectra. So super interesting.
Great, well, let's thank Natalia again.
Thank you.